All right, in this video, I'm going to cover the chapter 3.2, Neville data approximation and Neville's method. So think about the Lagrange interpolating polynomial. Okay, so a practical difficulty with Lagrange interpolation is that the error term is difficult to apply because as you can see that the f of x minus p the nx. Okay, let's say f of x is the exact function, and the p n x is the approximate polynomial using the Lagrange interpolating polynomial. So this is the bounded by the m over n factorial, right? And then the x minus x0 through the x minus xn. Okay, so what is m? M is the maximum, absolute maximum of the n plus 1's derivative of cosine of x. Oh, I'm sorry, here's the maximum. And then cosine is in the inverse a comma b. Okay, so so it's not I mean, so since we do not know f of x is an unknown function. So the therefore we don't know the n plus 1's derivative of f. Okay, so the degree of the polynomial needed for the desired accuracy is generally not known until computations have been performed. So we have to pretty much manually we have to increase the degree n of Lagrange interpolating polynomials, and then we find out the errors. Okay, so the common practice is to compute the result given from various polynomials until appropriate agreement is obtained. So as was done in previous chapter, right? So okay, so now then think about this. So we start from the P1, we compute this, and then we're gonna check the we're gonna calculate the error estimate, and then okay, then the error, the accuracy is not acceptable. Then we're gonna we need to find a P2 degree 2 Lagrange interpolating polynomial, and then we calculate the error estimate. We do error estimate, and then the accuracy is not acceptable. We find the P3. Keep going, right? Okay, into I don't know Pn and Pn plus 1. So now, but look at this. To find out P3, to find out P3, the information P1, P2, without, I mean, these two guys, I mean, we don't get any information, the information from P1 and P2. So whenever you want to calculate the P3, P4, and Pn, we have to build up from the P1 again. P1 is understand what I'm saying? So what that means? It means that for example, the work done in calculating the approximation by the second polynomial, for example, second polynomial, does not lessen the work needed to calculate the third approximation, nor the fourth approximation. Easier to obtain once the third approximation known, and so on. Okay, but I want to get I want to construct the list of this Lagrange polynomial as a get the I want to get the what the Lagrange polynomial interpolating Lagrange polynomial approximation recursively. That's the goal of in this chapter, and that is called Neville's method. Okay, so I want to get some kind of connection relationship between the P, for example, P2 and P3. So when we calculate P3, we can use P2 so that we can obtain P3 easier. Okay, so that's a goal. So in Neville's method, so you see definition 3.4, right? So let f be a function. Okay, defined at x0 through the xn. So as you can see, that x0 through xn are nulls, right? And then yeah, definitely we don't know function. We don't know the definition of f, but we do know the function value at these nodes. Okay, and suppose that what m1 through the mk are k distinct integer. Okay, distinct integer. Okay, so what does that mean? M1 through MK. What are they? Actually, M1 through MK are the sub indices in nodes. Okay, so I'll explain this one later. Okay, once I finish writing the definition. And then integers with mi must be between 0 to n. Okay, for each I. Then the Lagrange polynomial that agree with f of x at the k points are this. So then the polynomial that agree with f of x at the k points xm 1 through the xmk is denoted pm1 pm2 through the mk and x. So let me give you an example. So I know some of you may hard to understand that definitions, what it is. Okay, so think about this. This is the number line, I mean, x-axis, okay? So here's those, x is 0, maybe x1, x2, and x3, through here, xn, okay? So now we know that the function values at each node, right? So maybe this here, right here, and right here, and right here, right here, and right there. Okay, so the coordinate of that point is going to be x0 comma f of x0. Okay, and the coordinates of this one going to be xn comma f of xn. Okay, so now then, what's the m1 through mk? Maybe m1 through mk going to be, let's say m1 is, let's say 0, and then m2 maybe this is going to be, because see the m1 through mk are k distinct integers. Okay, so it means that all of the integers m through mk are distinct numbers, right? Distinct integers. So M2 must be maybe just 2, okay? And then M3, for example, M3 is just maybe 5, something like this, okay? So let's think about the this one, M1 through M3. So the K is 3, okay? So right here, K is 3. This, for example, all right? All right. Then P M1, P sub M1, M2, M3 gonna be P0, 2, 5, X. This is the Lagrange interpolating polynomial agree with that f of x0, f of x2, f of x5. It means that this is gonna be equal to this is equal to f of x0 times L L L2, okay, comma L2 what here L2 comma 0. Let me see. Give me a second. I wanna follow the notations, same notation as the index in the textbook. So give me a second. Yep. Okay. So yeah, they're gonna use the different the letter Q, but yeah. So but I need to explain about Q to use this. So let's just L2 let me say just L0, okay? So this is different from the notation what we have used in chapter 3.1. Okay, this is L0 of x plus f of x2, and then L2 of x, and then plus f of x5, and then L5 x. So these are just actually Lagrange polynomial Lagrange polynomial where, for example, L0x gonna be 1 when x is equal to x0, and then this will be 0 at other two nodes, x2 and x5. And then this one is a Lagrange polynomial where satisfying that what this guy is equal to 0 at x is x2, and then there's gonna be 0 at other nodes. Okay, so now then that means the P0, 2, 5 is a quadratic polynomial, interpolating polynomial, right? And agreeing with x is equal to x0, x2, and x. Let's say here's x5, for example, x5 right there. Okay, then the graph must be x like this, like this. Okay, so that's going to be P 0, 2, 5. So 0 to 5, this is indices. These are indices of nodes. Okay, so this one indicate that this P interpolating polynomial agree with that what? Agree with f of x at x equals x is x0, x2, and x5. Okay, so that's definition of the 3.4. So now the oops, give me a second. So let's see example then. Okay, so let's see specific example. Okay, so the example. This is example in textbook. Okay, example 4. Example. Let's see. Okay, so if the first one x0 is equal to 1, and then x1 is equal to 2, and then x2 is equal to 3, and then x3 4 and x4 is 6. Okay. And the second one, f of x is given as e to the x. Yeah, normally f of x is not given. Okay, but since this is example, so f of x is given. Okay, then the p 1, 2, 4 x. I told you what that means. 1 to 4. It means that x1. Okay, x2 means x2. 4 means x4. Okay, so that is equal to, I told you, f of the x1 times, we construct a Lagrange polynomial. But you know what? So 3 nodes are involved. So degree of Lagrange polynomial must be 2. Okay. So this is going to be x minus, this should be Lagrange polynomial. Well, this is Lagrange polynomial, second degree 2 Lagrange polynomial, satisfying that that one must be equal to 1 at x is x1, and then 0 otherwise, right? So x minus x2 times x minus x4, right? And then x1 minus x2, and then x1 minus x4, is it? And the plus f of x2 times x minus x1 times x minus x4, okay? And then x2 minus x1, and then x2 minus x4. And the plus f of x4, this is x minus x2, oh, I'm sorry, 1, and then x minus x2, and then x4 minus x1, and then x4 minus x2. Okay. All right. So, but let's figure out this one. So what's f of x1? F of x1 going to be e to the x1 is 1, right? So this is going to be e to the 1, right? X1 is 2. I'm sorry. So this is e square, right? This is e square times, and then x minus 3, and then plug in, a 2 and 3, right? And then 6, 2, 3, 6 into x1 to x4. Okay. Then we get this x minus 3, and then x minus 6 over 2 minus 3, and then 2 minus 6, right? And then plus e cubed, right? And then x minus 2, x minus 6, and then 3 minus 2, and then 3 minus 6, okay? And plus e to the 6th power times x minus 2, and then x minus 3, okay, and the 6 minus 2, and the 6 minus 3. Okay. All right. So now, next one, we're going to study, then now we're going to build up the Neville's method, okay? So we're going to study Neville's method, but to do that, we need to know the following notation, okay? So let me introduce that notation using my lecture note, okay? So, all right, so can you see this? Okay, so the method for, let's see, give me a second. Yeah, so okay, the method for recursively generating Lagrange polynomial approximation. Yeah, as you can see that from the name, title. So the goal is to generate Lagrange polynomial approximation recursively. Okay, so let f be defined as x0 to xk, and let xj and xi be 2 distinct numbers in this set. Okay, so xj, oh, wait a second. Yeah, xj and xi are nodes, distinct nodes, okay? So maybe, for example, xj could be x1, xi could be x3, okay? So now then p of x is equal to x minus xj times p0, 1 through k except for j. We know what that means, right? This is a Lagrange polynomial approximation, right? Is it Lagrange polynomial approximation agree with function f of x at x0 through xk except for xj, okay? And then minus x minus xi times, you see that here, p0, 1 through k, and then this is along the interpolating approximation agree with f of x at x0 through xk except for xi, okay? So, and divide by x minus xi minus xj. That describes the kth Lagrange polynomial. Okay, this is a Lagrange polynomial approximation. Lagrange polynomial. I'm sorry, Lagrange polynomial. Okay, so Lagrange polynomial approximation. So now then, you see stuff here. Then okay, now next one. So we want to prove that how the that P of x interpolate the f at k plus 1 points. I mean x0 through the xk. Okay, so I'll do this. Okay, so to do that, first we're gonna let's see. Yeah, we're gonna construct the we'll see. So here, this one we're gonna introduce the new notation q. Okay, you see the q. What is the q? Q is the Lagrange polynomial approximation. Agree with f of x at x0 through xk except for xi. So what's the q? Q is actually what? Lagrange interpolating approximation at what? K nodes, x0 through xk except for xi. And the q hat is Lagrange interpolating approximation at x0 to xk except for xj. Okay, so now then, so what's the goal? Goal is to show that p, what's the p? What's the p? Let's see. So what is p? P is what? P of x was what? This is equal to x. What is this? Let me see. X minus xj, right? Times p0, 1 through the j minus 1, j plus 1 through the k of x minus x minus xi times p0, 1 through the I, and then I minus 1, comma, and then I plus 1, comma, to the k of x, and then divided by xi minus xj. Okay, so this is a p, right? So here in this theorem, what P of x theorem says that P of x is the case degree k Lagrange polynomial that interpolate function f at nodes x0 through the xk. Okay, so then we have to prove that P of X agree with f of X at nodes x0 to xk. That's what we have to show there, right? Then we can say that this is the degree k along the point. Definitely degree, this is degree k, right? Why? Because this guy is what? P0 through the k except for j, and then P0 through the k and then except for I. These are what? Lagrange interpolating polynomial with degree k. Okay, so that's why P is degree k. So we don't have to show that this is degree k. Okay, so but we have to show that this one interpolate P of X interpolate f at nodes x0 to xk. Okay, so now okay, so now then, so here to do that, we first one we construct the Q and Q hat. Okay, so here's a Q and Q hat, and then now we have to show that Pxi is equal to f of xi, and then let's see, and then Pxj, yeah, Pxj is equal to xj, and then P of x k is equal to P of x is equal to f of x, and then where x is x0 through xk. Okay, so now the Pxi is what? I think I need to use the, let me show this one in sketch paper. I'll show you in the sketch paper, sorry. So, okay, so what was P of x? P of x is this one, right? See that P of x? Then P, let's see that right here. Okay, then P of xi, this is equal to, so plug in xi into x, what happened? The second term in the numerator going to be 0 because xi minus xi is 0, right? Now what about top one? Top one is going to be xi minus xj times this one of xi over, you see that? Denominator is what? Xi minus xj, is it? So xi minus xj going to be cancelled them out. So P of xi going to be P0, 1 through the j minus 1, j plus 1, and then through the k of xi. But you know what? This is a Lagrange interpolating polynomial. Agree, interpolating f at x0 to xk except for xj. Since I and j are distinct, so xi must be, what does that mean, x0? This is x0 means x0, 1 means x1, right? J minus 1 means xj minus 1, and then this is xj plus 1, right? This is means xk. So since I is not equal to j, I and j are distinct, so I must be in this list, okay? So maybe here xi is right there, or j plus 1 could be xi, okay? It means that this Lagrange interpolating polynomial is what? Actually interpolate the f at xi, right? So this is equal to f of xi. But before doing that, so we can express this one in terms of the new notation q and q hat. What's a q? Q. So this is equal to actually what? Q hat, right? Q hat xi. This is equal to f of xi. Okay. Why? Because q hat, we define the q hat as p0, 1, and then j minus 1, j plus 1 through the k. Okay, well, we just define q and q hat. Yeah, we'll see. Okay, so when you design the algorithm, yeah, we're gonna need to define q hat and q. Okay, so this is q hat right here, and then p of next one, p of xj. So we show that p of xj is equal to f of xj. It makes sense. Why? Because when you plug in xj into here, then the first term in the numerator going to be 0 because xj minus xj going to be 0. And then second term going to be xj minus xi times this one over xi minus xj. But you know what? Xj minus xi over xi minus xj going to be what? Negative. So we got negative p of, let's see. But you know what? So here we have one more negative sign. So negative, and then xj minus xi over xi minus xj going to be negative. So we're going to get negative times negative, which is positive. So p just p times 0, comma 1 to the I minus 1, and then I plus 1 to the k of xj. Okay, so that is equal to what? This is equal to q of xj. So what is it q? Q of q is defined by what? P0, 1 through d I minus 1, I plus 1 to the k. Okay, so since you know the same reason is here, I and j are distinct, so q xj must be what? Equal to f of xj. Okay, so now next one, what about other nodes? So p is a pxr. So r is the integer between 0 and k, and r is not equal to I and j. So here, so r is between 0 and k, and then r is not equal to I and j. Okay, then this is equal to xr minus xj times q hat, right? Q hat of xr minus xr minus xi, and then q of xr over xi minus xj. You can say that. Okay, so now that is equal to first one, q hat xr. Since r is neither I and j, q hat xr must be equal to f of xr, and then q of xr must be f of xr. Okay, this makes sense? Keep in mind this. What's a q hat? Q hat is Lagrange interpolating polynomial. I mean, Lagrange, the approximation interpolating f at x0 through the xk except for xj. Since r is neither I and j, this guy should interpolate f at x is xr. Same reason for this. Okay, so that is equal to f of xr. This is equal to f of xr. So we got xr minus xj. Okay, and then what? Let's see, f of xr r minus xr minus xi, f of xr over xi minus xj. Okay, so that this is equal to so f of x, look at the numerator. Let me simplify numerator. Okay, so f of xr is common factor, so factoring out. Okay, then xr minus xr, cancel them out. So we're gonna get the minus minus xi, which is positive xi minus xj. So we got xi minus xj over xi minus xj times f of xr. This is equal to f of xr. So we just proved that function p sorry. Okay. Okay. So I just proved that what function p, I mean, yeah, this p function p interpolate f at x0 through xk. Okay. All right. So now see. All right, so let's see lecture note. Oh, okay. All right, so theorem 3.5 implies that the interpolating polynomial can be generated recursively. How? Okay. So now I'm going to introduce Neville's method. Okay, using the based on the theorems what we just proved. Okay, Neville's method. All right. So Neville's method, CQ. So let's look at this. Qi comma j. What is this? Qi comma j. Here, first subindex I means end number, and then subindex j means degree. Okay. So what does that mean? End number. End number is the last the subindex of node. Okay. So for example, the Qi comma j means P of I minus j through the I. What is this I? I is what? Subindex of the subindex of node. Okay. So end number I means what? The subindex of the last node of P. Okay. All right. How many nodes here? How many nodes here? We subtract I minus j from I and then adding 1. That's going to be number of nodes in here, right? In that list. So I minus j plus 1. That's going to be j plus 1, right? Okay. So then that means P, this one is what? Is a Lagrange interpolating polynomial. Okay. Interpolating function f at x of I minus j x of I minus j plus 1 through xi. Okay, so this is the interpolating polynomial. Lagrange p is the Lagrange interpolating polynomial. Agree with f at j plus 1 node. So degree of p must be j. Okay, keep in mind this, and then keep in mind j must be less than or equals I. Okay. Okay, so that's the example. Now, let me see. So as you can see that P, yeah. So, all right, first one. First one, we're gonna what? We're gonna start from the degree 0 Lagrange interpolating polynomial. Okay. So P0. What is this? P0. P0 is what? Degree 0 Lagrange interpolating polynomial interpolating f of x0. It's simply just f of x0, right? Okay. The P1 is what? Lagrange interpolating polynomial interpolating f at f of x1. So P1 must be f of x1. So it's simply saying that P0, P1, P2, P3, P4 to Pk are just constants, okay, which are equal to f of x0, f of x1 through f of xk. Okay, at p sub 2 is equal to f of x2. Okay, and then we can express p0, p1, p2 as q00, q10, okay, and the q20. Okay, so keep in mind the second subindex in a q means degree. That's why all of the q expression using key in here, q here is 0. Okay. So now next one. So from these P0 to Pk, we're gonna construct the what? Degree 1 Lagrange interpolating polynomial. Okay, P0, what does the P0, 1? P0, 1 is a degree 1 Lagrange interpolating polynomial interpolating x0 and x1. Okay. So P then, let me, what? Give me a second. Let me show in a okay, stop. All right, so Q, oh, yeah, sometimes this webcam, the autofocus doesn't work. Yeah, it works. Okay, so now P0, what's P? P is what? What was this? So P P of X was X minus XJ. Okay. Times P 0, 1, J minus 1, J plus 1 through the K of X minus, okay, so minus X minus XI P0 through the I minus 1, I plus 1 through the K of X, okay, over XI minus XJ, right? Okay. So now, then what? Actually, let me see. So here, we're gonna apply this one to find the P0, 1. Okay, so P, so here X0, X1, X2, X3 through the XK, right? So for each node, we did construct the degree 0 Lagrange interpolating polynomial, which is constant function, right? P0, P1, P2, P3, right? There was a Q0, 0. This is a Q1, 0, Q2, 0, Q3, 0. Oops, this should be, that's right, this should be, I think the 0 is too big. It should be subindex. Okay, that is nothing but f of x0, f of x1, f of x2, and then f of x3, okay, and so on. And then now we consider the p0, 1 using q0, 0, q1, 0. Okay, we're gonna plug in q0, 0, q1, 0 in here. Okay, so now let's say what from here. Now, how can you apply this one in here? We just consider that I is give me a second. Okay, you just consider that I is 1 and J is 0. Okay, so to apply it right there, we consider that I is 1 and J is 0. Okay, and then okay, all right. So now then, just give me a second. So then we're gonna get this is P0, 1 is equal to, okay, this is equal to x minus x1, right? X minus x0, right? Times, the next one is what? Next should be p, what is this? Look at this. This is the Lagrange interpolating polynomial interpolating f, except for x is xj. So that must be what? Lagrange interpolating polynomial interpolating x0, interpolating f at only what? X, the xi, I mean x0, right? x0. So this should be what? The q1 comma 0, isn't it? P, give me a second. This should be I 1 P1. This. Okay, because the 1 is I, right? So that must be Lagrange interpolating polynomial interpolating f at xi. Okay, at xi. Because look at this. This is the Lagrange interpolating polynomial interpolating f at all of nodes except for xj. Okay, so here, this should be Lagrange interpolating polynomial interpolating all of node f, interpolating f at all of nodes. But how many nodes here? Just x0 and x1. We only consider x0 and x1. Okay, so that should be then what? Lagrange interpolating polynomial interpolating all of nodes, which means that x0 and x1 except for xj. Here j is what? 0. So this should be Lagrange interpolating polynomial interpolating f at xi, which is x1, x of 1, I mean, so p1. Okay. So now then this p1, but p1 is nothing but q1 comma 0, right? So this is equal to q1 comma 0. And the minus x minus x1 times p0. p0 is equal to what? q0 comma 0 divided by what? x1 minus x0, isn't it? Okay. All right. Now x1. Now think about p1 comma 2. p1 comma. Now you see that. So we need to construct the degree 1 Lagrange polynomial interpolating f at x0 and x1 using p0 and p1. So now we see that we are generating the one more degree Lagrange polynomial using the one less degree Lagrange polynomials recursively. Okay, so p1 comma 2 going to be x minus right here, x minus x1 times the p2 p2, right, which is a q2 comma 2 comma 0 minus x minus x2. Now you see pattern, right? 2 and the q 1 comma 0 divided by x2 x2 minus x1. Then what about this? P 2 comma 3 is equal to what? X minus x2 q3 comma 0 minus x minus x3 q 2 comma 0 over, okay, and then x let me see, x2, it should be x2, no, 2 comma 0, and then x2 x3 minus x2, right? So now p0 and 2 p2, yeah, and then now we're going to construct the degree 2. This is degree 1. This is degree 1 Lagrange interpolating polynomial. Now we're going to construct the degree 2 Lagrange interpolating polynomial. Okay. So now then, using the P0, 1, P1, 2, then we're going to consider P0, 1, 2. But actually, this is equal to what? Q2, 2, right? Why? Look at it. How can you figure out the sub-index of Q? The second sub-index in Q means the degree of that Lagrange interpolating polynomial, which is 2, right? Because 3 nodes are involved. And then what's the last end number? The end number? 2. Okay? So this is Q2, 2. Let's see. Let's see. One more example. This is P1, 3. This is going to be P using P12, P13. You see that? I'm sorry. P12, P13. Oops, 2, right? Okay. P12, P13. Then we can construct the P1, 2, 3. So what's this? This is going to be Q3, 2, right? Okay. So let's figure out Q2, 2. Q2, 2 is going to be x minus, now what? X0, right? X minus X0. Okay. So now then now we're gonna set the first sub-index as the what? J, and then last sub-index as I. Okay. Do you mind this? So this one gonna be J, and then last sub-index as I. All right. Okay. So then it's just gonna be x minus X0, and then Q what? 2, 1. Is it? Q2, 1. Why? What is Q2, 1? Because x minus X0, and then this must be what? Lagrange interpolating polynomial, interpolating f at what? X1 and X2. X1 and X2, right? X1 and X2. This is what? P1, 2, right? That should be equal to P1, 2. This is Q2, 1, right? Okay. The minus x minus X2 times, now next one, this should be Lagrange interpolating polynomial interpolating x what? X0 and X1. X0 and X1. Which is a Q1, 1, right? Okay. Divide by, okay, please, you need to practice this one by yourself, okay? All right. I told you, without completely understanding the algorithm, you cannot write the code. Okay. So I told you, coding is a what? Coding is the is done by your finger, not your brain. Okay, keep in mind this. So even though you understand in your brain, if you don't know how to write in a sketch paper from nothing, it means you cannot write code. Okay, always it's true. So the coding is done by your fingertip. Keep in mind this. So you need to practice. I'm doing this. It doesn't mean that you know that. Okay, keep in mind that. So Q1, 1, and then this is X2 minus X0. Okay, and then what is this? Q3, 2. This is going to be X minus X1, and then Q what? This means 2 and 3, right? 3, 1 minus X3, and then Q2, 1. over x3 minus x1. Okay, so let me stop here. Okay, so now I'm gonna continue to introduce Neville's method next time. Okay, so I'm gonna review this stuff, and then we're gonna get I'm gonna introduce a pseudocode of Neville's method, and then I'm gonna implement Neville's method to some examples in using the Octave online. Okay, all right, let me stop here.